Electronics. He's going to speak on the topic of a sensitive optical methods based on open source hardware technology capable of accurately measuring the refractive index of aqueous solutions. So if you are ready to present, you share, okay, already share your screen and let's start.
Good afternoon, all participants. My name is Konthee Boonmeeprakob. I am a master degree of the Division of Physics, Prince of Songkla University, and my advisor is Assistant Professor Dr. Chitadon Buranachai. Today, I would like to present my work on the topic is sensitive optical method based on open source hardware technology capable of accurately measuring the refractive index of aqueous solution. First, I would like to talk about the refractive index. The refractive index is the basic property of material. It plays an important role in the many industries. Its accurate measurement is often needed, such as in film technology, control quality in glass and plastic. And recently, it was reported the refractive index can relate to the concentration of the liquid media, such as the sugar in the water. There are many technologies to detect the solution concentration. However, optical method is widely used to determine solution by the measuring the refractive index, because contactless measurement avoiding the routine washing or sample contamination. Popular optical methods such as the refractometry, infrared spectroscopy, optical coherent tomography, but above technique that has the disadvantages such as it's expensive and require complicated equipment and people measuring transparent liquids. In my words, our method has the advantage is the high sensitivity, and we use inexpensive open part of software and hardware technology, and require only 100 microliters of the liquid sample. My objective has two objectives. First is to develop a simple method and set up for measuring the refractive index of an aqueous solution. Second is to measure the concentration of sucrose solution by measuring the refractive index with the developed setup. This is my sample chamber. The left-hand side shows the geometry of design of chamber, and the right-hand side shows a real picture. And a sample chamber is made by half of cylindrical glass and the transparent acrylic together with the front side tab, and by sealing with the epoxy glue. And there are the two holes, and in this side for use for the exchange solution. And you can see that in the white area is the micro channel chamber. Next one is my setup. We use monochromatic light source as the helium neon laser, which have the wavelength 632.x nanometer, and this has a direction of polarization as shown in this picture, and this is a vertical axis. And incident light direct into the glass and incident at the center of micro channel, and we mount it on the base at the base on top of a stepping motor with the axis of rotational passing through the light incident point. Therefore, the incident angle is changed simply by the rotational or stepping motor. Then the linear sensor array are used for the measure the reflected intensity of light at each incident angle. And there are two Arduino Uno for control the rotational of the stepping motor and the lead signal from the linear sensor. And this is the real picture of the setup. In this work, we measure the refractive index by finding the critical angle. For the internal reflection with the incident angle equal or greater than the critical angle, all the energy coming energy is reflected back into the incident media. This phenomenon called the total internal reflection. This we then form the Fresnel equation, and our vertical polarization axis is called the amplitude coefficient at the vertical polarization as say in this direction. Okay, and you can see this graph between amplitude coefficient and incident angle. When incident angle is higher, greater than the critical angle, the maximum, the incident intensity of light is the maximum, and the first intensity at have the maximum is called the critical angle, and this is the key of my method. And then when we get the critical angle, we can use the Snell law to calculate the index of refraction. We prepare the standard sucrose solution by dissolve sucrose in deionized water at various concentration, 10% to 50%. And the left-hand side shows the light intensity measured by the linear sensor array with various concentration in the microchannel. For comparison, we simulate the reflected light intensity by finding the square of the amplitude coefficient and use the refractive index data from the previous publication from the MISO. And for comparison, you can see the experiment data show the similar pattern, same left hand side, and increase of critical angle with increase of sugar concentration. Okay, you can see the first incident angle that have maximum in various concentration. And next, the measured critical angle were used to calculate the index of reflection from this equation, and the value shown in this table in this is my measured refractive index, and compare with the reported refractive index from MISO. The comparison of refractive index by our method is shown in the x-axis, and from the MISO shown at the y-axis. And it is confirmed that our method, despite being simple, is powerful and highly accurate. And next is the final report calibration graph between the concentration of sucrose and the measured refractive index. The plot shown in the figure shows the linear relationship between the sucrose concentration and refractive index, and this is show the equation, linear equation. That is the conclusion. We successfully to develop a novel and simple yet powerful method and set up capable can determine the concentration of the sucrose solution up to 50% by measuring the refractive index. And our method has the potential to determine the refractive index of an outer solution in the rank of 1.3234 to 1.4100. I would like to thank the Development and Promotion of Science and Technology Talent Project DPC and the Center of Excellence for Trace Analysis and Biosensor CAP COE and Division of Physics, Faculty of Science of Songkhla University. Thank you for your attention. If you have any question, you can ask.
Okay, time to questions. So in the chat rooms, we have several questions from Professor Sujit. Did you use a cylindrical prism, not triangular? Is it? Can you comment on the effects of the aberrations introduced by the curvatures of the prism? This is the first question.
Okay.
Because I think in this setup, it's better to use triangular prism rather than the cylindrical prisms because you're coming in at one angle only. But why did you use this curvature curve? It's not necessary there. You see, if I were you, I would use triangular prism.
The reason which I have the half of cylindrical gas because I want get the incident angle from the air, and in the gas is the equal incident angle. I want angle is the change from this effect. I use the advantage of the radius of the circle, and when you incident light into the half of spherical, incident angle is not changed if you focus at the center of the radiance.
Sure, but the light that coming out from the surface, you will have more than one angle. It will be a diverging beam.
Okay, because when the light is reflected light is coming out, I don't care about the incident light is coming out because we use the linear sensor array and measure the maximum of the angle, and I don't mind varies of the output incident angle, but we focus on the incident beam.
But surely you should see interference, right? You should see
Yes.
interference due to these coming diverging beam coming out of this prism. You wouldn't have a clean signal.
Yes, but I don't okay, maybe effect of the interference of the light coming out, but in the sensor we measure all of the interference, but we focus on the maximum of points in the sensor.
Yeah, I understand that. Then it's come to my second question. How can you precisely determine the theta C position? You're showing one result, right? Go forward a few slides more when you show your results, please. Yeah, this one. You see, this on the left-hand side, that is your measurement result, right? And how can you say like this is my theta C position? Because look at the noise level. It's not like a sharp cut, isn't it? Look at the transition at the critical angle. How can you like look at the purple one?
Purple one, okay.
Yep. How can you say which theta C that actually the theta C position? You see my question, right?
Okay, I see. Okay, but some concentration is the not smooth, and we focus on the first of the maximum incident angle that use the theta C.
Okay, so you're looking at the highest intensity level that comes first. Then you don't care about the fluctuation later, right? Because there will be a bit of noise after that, like fluctuation. There must be, right? It's not purely 100% light all the time. So it's quite.
No.
Yeah. Okay.
Yeah.
You didn't do any signal processing to determine the value.
No, I don't. Another thing.
Okay, then it's come to my last question. What is the sensitivity for this detection? Can you detect the change in third digits of refractive index, like from 1.33 to 1.3301? You see, this is the range that you're reporting is a range, isn't it? That you're detecting.
This range from we use from the concentration of sulfur solution, and the 0 is the 1.32 T4, and the 50 is the 1.41. This is the range of the measure.
Yeah, exactly. But it's you're missing one point, I think, which is the sensitivity of this detection. You didn't report the actual sensitivity. How small the change of refractive index that you can measure You didn't study that, do you?
No, I don't study that.
Okay, I see. Right, because that is quite important parameter for sensor, like what sort of changing in refractive index you can measure. Okay.
Okay.
I think that if you want to carry on doing this research, you should be focusing on the sensitivity as well, not just the range.
Dr. Sojit, do you ask him about the resolution of his research already?
Yeah, I have asked. Yes, it's about the sensitivity of this detection, because he didn't show any sensitivity.
But but in this method we prepare the unknown solution for use in the equation, but we prepare the 25 concentration weight by weight, and we obtain the value 24.65, and this is not shown in this presentation. This is my error from the linear links.
Okay, so in that error bar, what sort of scale in refractive index in that error bar that you show?
Okay, the error bar is from I repeat the T time to any very concentration.
Yeah, and what was the value? Yep, here we go. And measure refractive index. So you can measure plus minus 0.005. So that would be 0.001 RIU. So times 10 to the minus 3 RIU refractive index unit. So that is your error. Okay.
Okay.
That is respectable for total internal reflection measurement.
Yes.
Have you tried to study something like similar to this, like surface plasmon resonance sensor that people use it for measure refractive indices as well? Have you heard of it?
Yes, it's similar from SPR.
Yes. People use that for measure refractive index and giving a higher sensitivity than times 10 to the minus 3 RIU. People has achieved 10 to the minus 5 to 10 to the minus 8 RIU, which is more sensitive. Okay, if you carry on with this, I suggest you explore that options as well.
Thank you.
Okay, thank you, Professor, for so many questions, and thank you for presenter again. So, shall we move to another presenters? Okay, the next presenters will be